Let's take a look at the halogenation of alkenes. So on the left I have my alkene, and I'm going to add a halogen to it, so something like bromine or chlorine. And I can see that those two halogen atoms are going to add anti to each other, so they'll add on opposite sides of where the double bond used to be. Let's take a look at the mechanism so we can figure out why we get an anti-addition. So I start with my alkene down here, and I'm going to show the halogen approaching that alkene, so it's going to approach this way, and I put in my lone pairs of electrons like that. Now, if I think about that halogen molecule, I know that it's nonpolar, because if I think about the electrons and the bond between my two halogens here, both halogen atoms, of course, have the exact same electronegativity, so neither one is pulling more strongly, and so overall the molecule is nonpolar. However, if the pi electrons in my alkene, so I'm going to say that these electrons right here are my pi electrons, if those electrons get too close to the electrons in blue, they would of course repel them, since electrons repel each other, since they're like charge. And if the electrons in magenta repel the electrons in blue, the electrons in blue would be forced closer to the top halogen like that, giving the top halogen a partial negative charge and leaving the bottom halogen with a partial positive charge, since it's losing a little bit of electron density. Now I could think about that bottom halogen as acting like an electrophile because it wants electrons. And so in this mechanism, the pi electrons are going to function as a nucleophile, and the pi electrons are going to attack my electrophile like that. At the same time, these electrons over here, this electron pair on the left side of the halogen, is going to attack this carbon, and the electrons in blue are also going to kick off onto the top halogen like that. So let's go ahead and draw the result of all those electrons moving around. So now I have carbon singly bonded to another carbon like that. The electrons in magenta formed a new bond between the carbon on the right and my halogen like that. And these electrons over here I'm going to mark in red. So this lone pair of electrons on my halogen are going to form a bond with the carbon on the left like that. And that halogen still has two lone pairs of electrons on it. So I'm going to put in those two lone pairs of electrons, and that halogen has a +1 formal charge. This is called a cyclic halonium ion, and it's been proven to occur in this mechanism. If I think about that positively charged halogen, halogens are very electronegative and they want electrons. So the electrons in magenta, let's say, are going to be pulled a little bit closer to that halogen, which would leave this carbon down here losing a little bit of electron density, giving it a partial positive charge. And so that's going to function as our electrophile in the next step. And our nucleophile is going to be the halide anion created in the previous step, right? So we had a halogen that had 3 lone pairs of electrons around it. It picked up the electrons in blue, right? So now it has 4 lone pairs of electrons, 8 total electrons, giving a -1 formal charge, meaning it can now function as a nucleophile. So if I think about this cyclic halonium ion here, the halogen on top is going to prevent the nucleophile from attacking from the top. It's going to have to attack from below here. So this negatively charged halide anion is going to nucleophilic attack this electrophile here, this carbon, and that's going to kick these electrons in magenta off onto this halogen here. So let's go ahead and draw the result of that nucleophilic attack. All right, so now I'm going to have my 2 carbons still bonded to each other like that, and the top halogen has swung over here to the carbon on the left. It used to have 2 lone pairs of electrons. It picked up the electrons in magenta, so that's what the carbon on the left will look like. The carbon on the right is still bonded to 2 other things, and the halide anion had to add from below, so now we're going to have this halogen down here like that. And so now we understand why it's an anti-addition of my 2 halogen atoms. Let's go ahead and do a reaction. So we're going to start with cyclohexene as our reactant here, and we're going to react cyclohexene with bromine, so Br2. Now, if I think about the first step of the mechanism, I know I'm going to form a cyclic halonium ion. So I'm going to draw that ring, and I'm going to show the formation of my cyclic halonium ion. It's called a bromonium ion, right? So I'm going to form a ring like this, and the bromine is going to have 2 lone pairs of electrons. It's going to have a +1 formal charge like that. And also, I know from my mechanism, I'm going to form a bromide anion at the same time. So I'm going to have a negatively charged bromide anion like that. When I think about where that bromide anion is going to attack, I know that it's going to attack one of these 2 carbons here. So it could attack the one on the left, it could attack the one on the right. Let's go ahead and start with the carbon on the right and draw the product. So if a lone pair of electrons in the bromide anion attack this carbon right here, that would kick these electrons off onto the bromine, and we could go ahead and draw the result of that. So I would have my ring, and the bromine on top is going to swing over to the carbon on the left here. So now this bromine is going to go look like that. And the bromide anion has added from below the plane of the ring like that. So that's one possible product. The bromide anion could also attack the bromonium ion from the left side. So this lone pair of electrons could attack this carbon, which would kick these electrons off onto the bromine. And so we could go ahead and draw the result of that nucleophilic attack. So in this case, the top bromine would swing over to the carbon on the right, and it would pick up an extra lone pair of electrons. And the bromide anion, again, added from below the plane of the ring, like that. Now, these 2 molecules are actually different molecules. Let's go ahead and redraw them so it's a little bit easier to see. And we're going to stare down this way at the molecule. This is the top of your head. So let's go ahead and redraw that molecule. So this is the same molecule as if we're looking down on it. Right? If we're looking down on it, this carbon right here would be this carbon, and I can see there's a bromine coming out at me in space. So I'm going to put a bromine coming out at me in space at that carbon. I move to this carbon over here. That's this carbon, so there must be a bromine going away from me in space at that carbon. So that's one possible product. On the right, we do the same thing, right? So we're going to put our eye right here. We're going to look down. This is the top. So I can look at this carbon first, and I can see there's a bromine down at that carbon. So I go ahead and draw my cyclohexane ring. And at this carbon, there's now a bromine down. And of course, at this carbon over here, there's a bromine coming out at me, so I represent that with a wedge, and these are my products, right? And if you've already had stereochemistry, you know that these 2 products are enantiomers to each other. They're actually different molecules. They're non-superimposable mirror images. So we can see that the absolute configurations have been reversed. So if I think about this carbon right here, bromine coming out at me, bromine going away from me. This one down here, bromine going away from me, and for this one, a bromine coming out at me. So that's the halogenation reaction.